In this video, we're going to review some of the Maclaurin series, which are the tailored polynomials, but centered at 0, makes the Maclaurin series, and also some separable first-order differential equations. And this is going to give us a good review and set up to have the prerequisite knowledge to be able to do Chapter 16, which is a online-only chapter. If you've looked for it in your textbook, it's not in there. You have to look at it through Cengage or through WebAssign. Okay. First thing I want to talk about is the review of the Maclaurin series. So if you look at your textbook, and I've got it right here, this is page 674, there's a good list of the basic Maclaurin series. Probably the ones you're most familiar with are e to the x, sine x, and cosine x. And then some of the less common ones. 1 over 1 plus x, ln of x, arctan x, arsine x, and so on. Okay. We're going to talk about how to generate these. So what I'm giving you today is a review sheet to go over some of this stuff, and I want you to generate some Maclaurin series. So I'm going to do one of them for you. So let's say f of x is sine of x. And if we can remember how we generate a Maclaurin series, your f of x is approximately equal. I say approximately because usually we don't list all the terms in the series. The usefulness is that we only have to list a finite number of terms of the polynomial series, and that's going to be a good approximation for our function. But we take the nth derivative. It's actually, let's see, we add it all up, so we'll use a sigma. Actually, I'll make this equal, and we'll use all the terms. So equal to sigma, the nth derivative, evaluated at your center, I'm going to call the center A, times x to the n over n factorial. And n goes from 1 to infinity, or you could go 0 to infinity. Actually, let's start with 0. This will work if we start with 0, because we start with the very first term being where we're not taking a derivative at all. Okay, and since we go all the way up to infinity, then we can say equal instead of approximately equal. Okay, so I'm going to attempt to make a chart. Your n, your nth derivative evaluated at your center, and our center is going to be 0. Okay, and then actually let's do this. Nth derivative evaluated at x. And then after that, we'll do the nth derivative evaluated at the center 0. Okay. And then we'll put the whole thing together. Okay, so we've got n. This will be nth derivative valued at 0 times x to the n over n factorial. Okay, so n will be 0, 1, 2, 3, 4, 5. Let's just do 5 terms. Okay, so the 0 derivative is just f of x, which is sine x. And n is 1 is the first derivative, which is cosine x. Second derivative, negative sine x. Third derivative, negative cosine x. The next derivative will be positive sine x. And then cosine x. Now evaluating these derivatives at 0, sine of 0 is 0. Cosine of 0 is 1. Sine of 0 is 0, cosine 0, negative 1, 0, and 1. Now, if you'll notice what happens with this particular series, anytime you're taking an even derivative, your nth derivative is 0. So you're only going to have terms for the odd terms. By putting it all together, the nth derivative, so we want this thing, that's just going to be 0. We've got 1, x to the first, over 1 factorial. You've got 0. You've got negative 1 x to the third over 3 factorial. And we've got 0. Then we've got positive 1 x to the fifth over 5 factorial. Okay. So you probably remember seeing this. Your sine of x is equal to f a plus f prime of a, x to the first over 1 plus f double prime of a x squared over 2 factorial plus f triple prime of a x to the third over 3 factorial plus the fourth derivative, value of a x to the fourth over 4 factorial plus dot, dot, dot. So sine of x is going to be equal to, this one is just 0. Remember, every other term ends up going to 0. This one, you just end up with an x. This becomes minus x cubed over 3 factorial, and then plus this one over here is going to be x to the 5th over 5 factorial. That comes from these terms over here. Okay? And then you end up with saying sine of x equals, you could say, plus dot dot dot, or sigma n equals 0 to infinity. Then we have to figure out how to write this. So if n is 0, we're going to x, we have -1 to the, let's see, what do we want here? The first term is 0, so we'll say to the n. And we've got x to the 2n plus 1 over 2n plus 1 factorial. Okay, just make sure that works. When n is 0, that's a 1. X to the first, we've got a 1 factorial. When n is 1, we're going to have a negative, which is correct. We'll have x to the third over 3 factorial, and so on. Okay. Now, I'm not going to go over all of these. I do want to give you a small hint, or remind you a couple of things. If you have the series for 1 over 1 minus x, okay, this one you can think of, remember, for a geometric series that converges, your infinite sum was your first term over 1 minus r, and this will converge to this value whenever your common ratio is between -1 and +1. Okay, so you can think of this as this sum. For your first term, t1 is equal to 1, and then your common ratio is x. So this would be, first term is 1, plus x squared, plus x cubed, plus dot, dot, dot. Or you could say this entire series is equal to n equals 0 to infinity. Actually, let's just go 1 to infinity. Actually, let's do 0 to infinity. And then you've got x to the n. That's all you've got. Because x to the 0 is 1, and then x to the first, x to the second, x to the third. Okay? So using that idea is going to help you do some of these other questions. Some of the other questions when you have something like, let's take a look. Go to the other side, but let's say you have something like number 1e. So tan inverse of x. Where do I begin? So just a hint, we know that the d dx of tan inverse of x is equal to 1 over 1 plus x squared. Okay, so this one looks like the last one. You could turn this into a geometric series where your first term is 1, your common ratio is -x squared, and work from there. Okay. I'll leave the rest to you. You can find some hints if you look at my answer key as you try to work through these. But I want to go over one question. So number 1 on the back side of the worksheet, which is, consider the differential equation dy dx, which is equal to xy over x squared plus 4. Right? Now, a differential equation is any equation that has a derivative in it. Okay? This is called a first-order differential equation because we only have a first derivative. Okay? It would be second order if there was somehow like a second derivative of y and maybe a first derivative of y. You look at the highest degree, the highest derivative, and that would be the order of your differential equation. This is just a first order. The reason I'm reviewing this one, you might just remember how to do this, and if you do, you can skip this. But when you have a differential equation, if you're able to separate the variables, you want to separate the variables, and then you integrate both sides. Okay? So we'll get the dx over here and move the y over here. So we're going to have dy over y equals And then on the right side, you've got x over x squared plus 4 dx. Okay? So now we can integrate both sides. The antiderivative of this is going to be ln of y, which is equal to, in this one we could do a substitution. So let u equal x squared plus 4. du is going to equal 2x dx. So x dx is going to equal du over 2. So when we rewrite this, this becomes, we'll take out the 1/2. So the 1/2 du replaces the x dx. And then we've got 1 over u. So 1 over u du. Okay. So the antiderivative of that, ln of y equals 1/2 ln of u. So u is x squared plus 4. Really, this should be an absolute value here. We don't need an absolute value because we know that's positive. Okay. And then sorry. And don't forget the plus c. We would have a plus c over here and a plus c over here, but I can combine them onto one side plus c1. Okay. When we rewrite this to get the y by itself, so we do e to this entire thing is going to equal y. Actually, before I do that, let's do this. Equals. This 1/2 gets bumped up here as an exponent, so natural log of the square root of x squared plus 4 plus c1. So we get y equals e. So e to this entire thing, e to the natural log of rad x squared plus 4 plus c. But if there's a plus c up here, we could say times e to the c1, which just becomes its own constant. So y equals e to the natural log of this, we just the square root, x squared plus 4 times this thing, which is a constant, so we'll just call that c. Okay? And that is the answer for part A. Okay? In part B, they give us an initial condition. They tell us that find the particular solution, so 0, 4, so you can plug that in, plug in 4 for y, plug in, we're going to solve for c. So x squared, so we just get square root of 4. Okay. So 4 equals 2c, and c will equal 2. So we get the particular equation, 2 rad x squared plus 4. In part C, asked for a domain and range. Your domain, x can be anything. So domain, you could say all real numbers, or you could say set of all x. The range, well, smallest x can be is 0. So even if that's negative, when you square it, it becomes positive, so you get 2 times 2. So the range is anything greater than 4. Set of all y such that y is greater than 4, greater than or equal to 4.